Hello, everyone. This is question 3 of the 2019 test 3. I told this question that a reaction occurs in a voltaic cell given by this notation that I've just written down here. Now, part A wants you to write out the half cell reactions and the overall one. So you know from here, first of all, when in cell notation, you start out with anode, cathode. So the first thing we have is the anode, and the reaction happening there is oxidation. So in that case, we have magnesium going to magnesium 2+. It's written in the direction that it is actually occurring. We balance this, 2 electrons. Now the other side is our cathode, and that is our reduction reaction. So it's going from silver plus to silver. In order to balance that, we need to have 1 electron. I'm going to add the 2 together. I want to get rid of those electrons. So multiply everything here by 2. You can go through here. You have magnesium. It's 2 Ag plus going to 2 Ag plus Mg2+. So there's each of your half reactions and the overall one. Now, part B wants you to draw a picture of this voltaic cell and label everything. First of all, our voltaic cells, we always have 2 beakers, solution. We always have an electrode dipped in each. So let's draw our 2 beakers. And you could probably make a much prettier drawing than me. They are connected a wire through a voltmeter, and we also need to have a salt bridge to allow the flow of charge or ions between each solution. So this one on this side will be our anode. So looking at our reaction, our anode, the solid portion of it is magnesium. So this is an active anode. It means that it is actually participating in the oxidation reaction. That's there. And in the solution, we are going to have the magnesium 2+. And what's happening in the reaction is that the magnesium is turning into magnesium 2+. It's being oxidized, kicking out magnesium 2+, and also generating electrons from our half reaction that we drew. So those electrons are coming up this way. So this is our flow of electrons from anode over to the cathode. Here's our cathode on this side. So our cathode, our solid portion, is silver. So it is an active electrode because it's actually participating in the reaction. And in solution, we have Ag+. In this case here, our Ag+ is being reduced and converted into Ag, picking up one of those electrons in the meantime. So we also have negatively charged ions floating around in here. Doesn't matter what they are because they're not participating, just there for charge balance. And getting to charge balance, we also have to figure out what's going on in our salt bridge, because remember, the salt bridge is what will funnel either negative or positive charges to either beaker depending on what's needed. So over here where we're generating magnesium 2+, it means we're increasing our positive charges in this beaker, which means that to overcome that, you need to have some negatives flowing in. So we're going to have the negative ions in this salt bridge moving in this direction. And over here, you're losing those positive charges as they're being consumed to make the silver. So in that case, you need to replace those as our negative builds up. Well, actually won't build up unless you want them not even happen unless these positives come over to maintain that charge balance at all times. And I think that's all. You can label this as a salt bridge. But besides that, that looks pretty good. Now, part C, almost done this question. So part C wants to know E cell at 298. And they're also giving you a value for E naught cell, which is going to be 3.17 volts. Okay, so our equation for E cell, E not cell, minus RT over NF ln of Q. So in here, we know E naught cell, that's given to us. R, that's our 8.314. That's joules per mole Kelvin. We know 298. N is the number of electrons transferred in the balanced equation, which I've erased now, but that was 2 electrons, if you look back up at part A. We know Faraday's. Now Q, this is coming from our balanced equation. So from part A, we know that that is going to be the concentration of magnesium over the concentration of silver plus squared, because it had that stoichiometric coefficient of 2 in front of it that shows up in the reaction quotient equation. So these numbers we're getting directly out of our cell notation. In concentration cells, they're actually telling you what those concentrations are. So 1.3, that's 1.0001 squared. So with all these values, you should be able to come up with an E cell value of 2.96 volts. Now it's important when you are doing these, don't do them just like what I did here. Make sure you show all your work, put all of the values in there, show all your units, and make sure that things are canceling out in each case. And that's the end.